Here's a quick overview of probability distributions or distribution functions. That's the general term, and we're talking about the distribution of the values that a random variable can take on. And here's a distribution for a random variable x. This could be any number of things. We talked about the sum of two dice, right? That's a discrete random variable, and it has a symmetric distribution that looks something like this. When we're talking about discrete variables, we're talking about probability mass functions, or PMFs. And so this distribution is called a PMF. And what it shows us is the actual probability or fraction of a particular value of x occurring. And so what we can do is say, okay, what's the probability that x equals 2? Well, we just plug in 2 into this probability mass function, which is really just a graph, and we can come up with a value. Say that's 0.3 right here. All right, so that just equals 0.3, and that's our probability. Now, if we sum all these up, they should sum up to, you guessed it, 1. So if we sum up all the potential probability masses or probability that x can take on, that should sum up to 1. And hopefully that does for this example as well. So that's our distribution for discrete random variables. And let's go down and look at cumulative distributions. And for discrete variables, this is a step function. And for that same example, we did have a real probability for 0 that you see right here, so 0.1. So that's where we start at 0.1. We come across, and then the value, or x, cannot take on anything between 0 and 1. It's discrete. It can't be 0.5. It's not a continuous variable. So from 0 to 1, the probability is 0.1. I have an open circle there. And then we jump up to the next probability. So we're just adding up. So cumulative distribution functions add up the probabilities from one value of the variable to the next. So then we add up, I think it was 0.2 is what we added, from 1 to 2, open circle, and then we jump up between 2 and 3 to the next probability. So all I did is just added up 0.1, 0.2, and then 0.3. And that brought us all the way up to 0.6 right here. So it's a cumulative adding up of probabilities, and we draw it this way because we can't have values between these discrete values. So the way I evaluate that is the probability that x is less than or equal to a particular value that we're interested in. And then we write that as big F of x. So big F means cumulative distribution. And we evaluate that at 2. And then what that means mathematically is that we're just summing up our individual probability masses. So that's back up here, right? The probability mass function. We're summing up those individual values from 0 to that particular value. All right, so cumulative distribution function, CDF, and we denote that as big F of x. Now let's go over to our continuous variables. And this is represented as a histogram. First of all, we'll start with a histogram, and then we'll go into a continuous function. So first, I have plotted here relative frequency. And this is where if we have a range of values from 0 to 2.5 for our x, then we can bin those values, and we have a bin with a width of delta x. And that's the same width as we go, right? It's just 0.5 in this case. And then what I'm saying is, well, let's take all those values, and then let's see which values fall between our bins, and then divide the number of values by the total number of observations. So n sub I is the number of values that fell between 0 and 0.5. And then we divide by the total number of observations, and here we get 10%. All right, and we do that for all the range of observations. That gives us a histogram. And then we have our relative frequency plotted on this y-axis, just the number of observations that fell in each bin divided by the total number of observations. And we'll note that if we sum up all of these values, our relative frequencies, then we get to 1. This is the same as that probability mass idea. But let's take this a little bit step further and define probability density, which we denote as little f sub big X evaluated at X. So that's that's the way we say probability density. And I'll just write that up here. Big X. So big X represents whatever values our random variable can take on. It just represents the overall random variable. And then little x is some particular value of that random variable. So what I've done here is you'll notice that the y values are a little bit different. In this case, they have a units of probability density. And to calculate that, all I did is I take over here, I take the relative frequencies, so n sub I divided by n, and divide by the bin width, delta x. So that gives me probability density, units of probability density. Same values on the x-axis, but now I've got these different values on the y-axis. And so to evaluate this now, I'm thinking of what's the probability that x falls between some value. And then I can say, well, that's going to equal to the probability density function at that value times delta x. So we're basically taking the probability density at a particular value, multiplying it by the bin width. And then in this case, we get back out our probability from above. So in this case, the density was 0.2, and then the probability is 0.1 for x falling between those values. And we'll note that if we sum up all of the probability density values multiplied by delta x, we get 1. And what that means is the area underneath this histogram, which is this right here, all of that area sums to 1, which should make sense. It's the area under this density function is the total probability, which is always 1. So let's take this over to continuous functions or smooth curves. So same, this is a PDF now, and this is a continuous function. So this is basically delta x going to 0, and then we get a continuous function. You're basically kind of integrating, or anyway. So this could be, so we've heard of normal curves. We've heard of, there's a lot of different functions that this could be. We have probability density on the y-axis and the range of values that our random variable x can take on. And this represents, just like the histogram, the distribution of values of x. What are the potential values that x could have? So for a continuous variable, the probability that our random variable, big X, right here, takes on some value, little x, is equal to 0. And this is because, back in that example, if we define x as some value, it can have really infinite precision, right? And so the probability that it's going to line up perfectly is 0. So we evaluate probabilities over intervals. What's the probability that x is less than or equal to some value a? Or what's the probability that x falls between some interval? And to do that, we integrate. And by integrating, we end up at the cumulative distribution function, big F of x. So capital F of x. And capital F of x is equal to the integral of our PDF right here, little f of x, dx. And let's just talk about what that means. I'm going to zoom out and bring back in our PDF. What that means is that, say this is 0 up here, and I want to evaluate the probability that x is less than or equal to some value a. Then if this is a, what I'm doing is I'm going to integrate this curve up to that value, which then gives me the area. So the probability that x is less than or equal to a is just the area under the curve up to that value. What the cumulative distribution function does is, if this is an actual function, say just like some parabola or something like that, then by integrating that, I get this curve. So this is what the integral looks like for the PDF up to the maximum value of x, which this integral brings us all the way up to 1. That's the area under that curve should equal 1 if you go all the way to the extreme value of x. So I'll just make this a. And if we evaluate the cumulative distribution function at a, then it gives us the area under the PDF up to that point. So say that's just 0.2 or something like that. This is the cumulative area under the PDF up to A. And you'll notice that it's kind of not very steep, and then it gets really steep, and then that maps with our curve up here, where we have a high density of values in the middle. That's where our probability increases pretty dramatically. So this S curve is just a cumulative integral up to some particular value of interest, and that's how we interpret it.